Welcome to Unit 4 of this course. The name of this unit is Regular Properties. We will understand what this means during the course of this unit. In the previous 3 units, we have seen an idea of model checking and an idea of how to use the tool NewSMV. As of now, you are in a position to describe the model of a system in NewSMV, write some simple requirements like G, F, etc. and you know how to check these requirements on the model. Given that you have a fair idea of what model checking is, I will now give you a plan for the rest of the course. This is what I was saying. We have been modeling code as transition systems with states and transitions between them. In order to be able to check properties, we defined what are called atomic propositions, and then they are evaluated on each state. We had defined atomic propositions P1 and P2 for this transition system in the previous unit. P1 was the atomic proposition which checked if request is 1, and P2 was the atomic proposition which checked that the status is busy. This is a model. To check requirements, we had defined operators G, F, X and GF. G of some expression will ensure that every execution of this model satisfies this expression in each state. F was the requirement which said that in every execution there is some state which satisfies the expression. X of an expression will say that the next state satisfies the expression, and GF expression says that in every execution the expression is true infinitely often. We know how to enter the model and the expression in the format of the model checker NewSMV. We have seen examples where NewSMV says that yes, the property is true on the model, or no, the property is not true, and if it is not true, NewSMV gives you a counterexample trace. This will help you to make necessary changes to the model. The question that we ask now is, what are the algorithms used inside NewSMV for checking these requirements on transition systems? We just know that NewSMV does something and gives out an answer. We have seen the algorithm for the simple case of an invariant, but now we are interested in algorithms for checking these generic requirements. Although usage of model checkers is simple, there is a lot of work that has gone in the designing of model checking algorithms. While designing algorithms, there is a major challenge. This is what I am going to explain in the next slides. Let us recall the interleaving operator for transition systems. Suppose this is a transition system, this is yet another transition system. Now we want to talk about the joint behavior of these two transition systems. We have been doing this quite frequently over the last units. Remember that we have been writing modules in NewSMV and we have been reusing them multiple times. in the sense that we have composed them either synchronously or asynchronously. In the case of asynchronous composition, we use the keyword process. By now, the usage of process should be clear. If not, you can have a look in the previous 2 units. While doing this, we are essentially computing the interleaving of transition systems. So let us now recall the definition of interleaving. There are 3 states in this transition system, L1, L2 and L3. There are 2 states. So this transition system can be in either Q1 or Q2. When we want to talk about the joint behavior, we want to track the states of both these systems. So we need to maintain the current state of both of these systems. This gives us the following states in the joint behavior. The joint system can be in either L1, Q1, which signifies the fact that this system is in L1, this system is in Q1, or in L1, Q2, L2, Q1, L2, Q2, L3, Q1, L3, Q2. How many states did we get? For each state here, we have a state that contains a state of the other transition system. So in all, we have 3 times 2, 6 states. Once we have given the states, we can then define the transitions as follows. At L1, Q1, either transition system 1 moves or transition system 2 takes the next transition. This is the transition which signifies that this transition system has taken the next transition. This is a transition which signifies that transition system 1 has gone to the next step. This is fairly standard, and we have explained how to construct the transitions in a previous unit, so you can have a look at it. The main point that I want to recall is that the number of states in the interleaving is going to be the product of the number of states in this transition system and the number of states in this transition system. This is what I was explaining in the previous slide. If you have TS1 and TS2, TS1 with N1 states, TS2 with N2 states, the interleaving will have N1 times N2, N1.N2 states. If you continue this argument, what you will see is that suppose we interleave K transition systems. TS1 has N1, TS2 has N2, TSI has Ni, and TSK has Nk. The number of states in the interleaving is going to be the product of N1, N2, Ni, etc. I mean N1 times, N2 times, N3 times, so on till Nk. So assume that there are 10 transition systems. Each of them have 10 states. Then the interleaving would have 10 to the power of 10 states. Here it looks simple. Each transition system has just 10 states and we have just 10 transition systems. But when we want to look at the joint behavior, we will do an interleaving, and the interleaving will give us a transition system with so many states. This phenomenon is called state space explosion. Checking requirements on the transition system works by computing all the reachable states. When we have so many states, the algorithms need to be extremely efficient and they need to use very efficient data structures. Otherwise, the computation will take a long time, and there are situations where the computation does not stop even for weeks. The models that are available in the industry, they are huge, and hence when you compose them, you get a lot of states. A good amount of research has gone into tackling this state space explosion problem, and new SMV can currently handle more than 10 power 120 states. The question is, what does new SMV do in order to tackle state space explosion? We have asked two questions. Question 1, what are the algorithms used for checking requirements on transition systems? And question 2, how does our tool new SMV tackle this problem of state space explosion? We will try to answer these two questions in the coming units. This forms the plan of the course. Here is a more detailed course plan. In the first 3 units, we have seen what transition systems are, how to model code as transition systems. We have seen examples of requirements that can be checked on transition systems, and we have seen how to do it with new SMV. This part is already a trailer for model checking. You can already start using model checking with these ideas. Now, in the coming weeks, what we will do is, we will first try to generalize these requirements into something called LTL, Linear Temporal Logic. If you remember, in new SMV, when we were checking it, we were using the command check LTL spec. We will slowly see what this LTL means and how these LTL formulas are checked on new SMV transition systems. This will form units 7 and 8. However, in order to be able to understand the algorithms that new SMV uses, we need some preliminary concepts. They will be handled in units 4, 5 and 6, and these concepts are related to automata. We will see what they are in a gentle way. After this, in unit 9, we will see other kinds of properties. So far we have seen linear time properties. There are other kinds of requirements that one may want to check, and these are called branching time properties. We will again see in unit 9 what they are. And finally in unit 10, we will see how new SMV handles state space explosion. This is not going to be the end of the course. In the next 5 units, unit 11 to 15, we will see an extension of transition systems where timing and probabilities are introduced. That will be a new section entirely. This is the plan for the first 10 units. If at some point of time you think you are lost, I would urge you to come and have a look at this slide. This will give you a broad idea of what we intend to do in this course, and the units are just plugging in details to every topic. Already I hope that the first 3 units would have given you a good idea about what model checking is, what are its challenges, and a curiosity to know what are the algorithms that are used in model checkers.